Hello everyone, I am Dr. Ritish Kumar from Ajay Kumar Garg Engineering College. So let's begin the topic, that is microstrip line, and the subject name is microwave and radar engineering. So I will cover the topic of microstrip line, which is the most important topic. Microstrip line is a kind of transportation media through which RF signal transmit from source to load. That is the basic transportation media. So let's begin. So transmission line, first we start from the transmission line. So classification based, we can divide into two forms. The first one is the geometrical point of view, we can say. So in geometrical point of view, we have two kind of transmission line. The first one is a multi-conductor based transmission line, and second one is the single conductor based transmission line. And secondly, we can characterize in terms of mode, such as TEM mode or non-TEM mode. So here here I represented a kind of transmission line. The first one is the coaxial cable transmission line, and second one is the waveguide. So you can see here this transmission line having two conductors. The first one is the inner conductor. This one is inner conductor, and this one is the outer conductor. So if we correlate the thing in between these two transmission lines, so here we can have a single conductor. This transmission line is designed only based on the single conductor. Here we have more than one conductor, the inner conductor and the outer conductor. So here the geometrical point of view, we have these two kind of transmission lines. Secondly, the TEM mode and non-TEM mode. So here we defined non-TEM mode, we have TE, TM and HEM mode. TEM mode is nothing but a transverse electromagnetic mode, and non-TEM mode such as T, that is transfer electric mode, transverse magnetic mode, and we have another kind of mode, that is hybrid electric magnetic mode. Here we define structure of microstrip line as well. So this is also having more than two conductor, where we have the center conductor here, and this one is the ground conductor. So we can say microstrip line also has the multi-conductor based structure. So in the next slides, we will discuss about various kind of mode, that is TEM mode. TEM mode is a transfer electric mode, transfer electromagnetic mode. So we have electric and magnetic field are perpendicular to with each other. Also it has both has the perpendicular directions with the propagation. So in that case, we have Ez is equal to 0 and Hz is equal to 0. So as name suggests, transverse electric magnetic mode. So if the propagation is in the direction of Z, so the transverse component would be X and Y. So in this case, we have Ex, Ey, Hx and Hy component would be present in the case, while Ez and Hz always be equal to 0. So if we talk about the TEM mode, that is transverse electric mode, there should be some condition which needs to satisfy. The first one is the at least two disjoint conductors should be present in the transmission line, such as we discussed such as coaxial cable, and apart from that we have strip line as well. Now secondly, to have a pure TEM mode, the medium surrounding the central conductor should be the homogeneous, isotropic and lossless. This is the main two condition to have a pure TEM mode or perfectly TEM mode, we can say. So next one is the TE mode, that is transverse electric mode. As name suggests, transverse electric mode. So only the transverse component of electron mode will exist. If we talk about the propagation is taking place in the Z direction, so in TE wave only E field is purely transferred to the direction of propagation, and magnetic field is not purely transverse. So in that case, Ez always be equal to 0 while Hz is not equal to 0. The second one is the TM mode, that is transverse magnetic mode. So these two mode are complementary by nature. So all the things is replaced by electric field is replaced by magnetic field. So so in the case of TE wave transfer electric mode, H field is purely transferred to the direction of propagation and electric field is purely transverse. As we have mentioned here, Ez is equal to is not equal to 0 while Hz is equal to 0. So these are complementary by nature. As we have here hybrid mode. Hybrid means both T and TM waves are coupled together. In that case we have Ez is not equal to 0 while Hz is not equal to 0. Sometimes hybrid modes are called as EH and HE mode as well. This is all about the mode that we need to understand to classify the transmission line. So this is a planar transmission line. As we mentioned two transmission line here, the first one is the strip line and second one is the microstrip line. The use of my planar transmission line is it has a small size and compatible with the IC technology. Suppose if we design a microwave circuitry over where several components such as amplifier, rectifiers, mixers and low noise amplifier, etc. So we need to design us microwave ICs, for which we need to have a kind of microstrip line design through which we can minimize the size of the microwave ICs. So we can see a small size and compatible with the IC technology is the biggest advantage of this microstrip line. So here the first I will discuss the strip line. So in the strip line, as you can see here, there are three conductors. So we can say this is a multi-conductor transmission line. So here this is a center conductor which has the width of the center conductor V, and this center conductor is surrounded by some dielectric media, and this one is the ground plane. Both are the ground plane. And the thickness of this media is represented by V. So here we find that initially in the last slide, as we discussed, that for the condition of pure TEM mode, two conditions needs to be verified. The first one is the at least two disjoint conductors should be present, and the medium filling surrounding the center conductor should be isotropic, homogeneous and lossless. So in the case of strip line, you can see at the surrounding the center conductor, the media is homogeneous, and the first condition, at least two disjoint conductors should be present. So both conditions are verified here. So we can say this transmission line, that is strip line, have the pure TEM mode, we can say. While in the case of microstrip line, you can see here this is a center conductor, and this center conductor and this one is the ground plane here. So again, if we correlate the thing, or we can consider here at least two disjoint conductor present here, while the second condition is saying for the pure TEM mode is the surrounding medium around the center conductor should have the homogeneous by nature. But here we find that the upper section of this is center conductor having the air media, while the lower section is having the relative permittivity media, that is epsilon r. This part of the transmission line is called as substrate. So this is nothing but a substrate. We can say this is a kind of dual side PCB where a perfect ground plane is mentioned over here, and if we etching out some ground plane over the other side of the PCB, we have some kind of transmission line or other kind of structure as well. So this is about the microstrip line. So due to the not having the homogeneous surrounding medium around the center conductor, so this kind of microstrip line have the quasi TEM mode. So this is the main important point that we need to highlight here. The strip line has the pure TEM mode, while the microstrip line has the quasi TEM mode. Now the thing is, suppose this is a strip line, we can image this strip line with the coaxial cable as well. Suppose this is a center conductor, this one is the outer conductor, and this is the center conductor, this one is the outer conductor, and here in between these two the media is dielectric media, that is called Teflon. So yeah, if we correlate this thing with the strip line, so if we cut these two sections from this point and through this point, we have the similar structure as we have in the strip line. So as we know that the electric field distribution in coaxial cable is looking like in this way. So this is a kind of pure TEM mode. So we can say coaxial cable is also having the pure TEM mode. The electric field distribution of the strip line is shown here. Here the solid line is representing the E field and dotted line is representing the H field, right? Now the thing is, all the electric field is going from center conductor towards the outer conductor, that is the ground plane here, and it is looking like the similar pattern as we have in the coaxial cable. So we can say this one is a pure TEM mode again. Now here you can observe here the field distribution, electric field distribution is going downwards, which is going through the substrate, and some part of the electric field is going in the air. So actually the thing is, this is the relative permittivity is defined by epsilon r, and we know that the relative permittivity of the air is the lowest one, that is 1. So as we know that most of the electric field is confined in with more in the high dielectric regions, that's why most of the electric field is confined in the dielectric region, which has the relative permittivity more than 1, or we can say epsilon r air. So the thing as we can say here, this one is the interface of two dielectric media. The first one is the air and second one is the substrate permittivity having the epsilon r equal to something value. We can have substrate like FR4 substrate, RT duroid, Roger, and Teflon, etc. You can consider here according to your application. You can choose it. So this interface having this kind of bending nature of electric field. This bending nature of electric field at the interface of the two media is known as fringing field. This is known as fringing field, and this fringing field is main cause of the radiation. So in some terminology, radiation is required, such as in the case of antenna application, radiation we need to highlight it. But if we design a component, microwave component, so our main aim is to have radiation loss. Radiation should be as low as possible. How to make it the radiation as low as possible? If you take the epsilon r, that is relative permittivity, as high as possible, then most of the field are confined in between this substrate. So this can be reduced by taking the high relative permittivity of the substrate. Now the uh, thing is suppose I am taking this one is the resultant vector of this field. So this field having two component, that one is, suppose this one is ex, this one is ey, and this one is ex, suppose, and this one is the resultant electric field. So this electric field is mainly cause of having the surface wave as well. In superficially, I am telling you, this one is the main cause of having the surface wave. Surface waves always occurring at the interface of the two dielectric media, that is represented by this one, this interface. Now this is main basic point regarding the microstrip line and strip line here. Now the second one is microstrip transmission line. As we discuss all the things that we have mentioned here, suppose this is a multi-conductor device, the rest of the thing that is remained here, because the upper part is having the air dielectric constant and lower half is having the some substrate permittivity, and both, because this is epsilon r is equal to 1 and this one epsilon r is greater than equal to 1. So both are having the phase velocity, upper part having the phase velocity is different from the lower part. So this is the another point that we need to highlight here. The secondly, now we will discuss about the thing is the designing equations. So what we need to focus here to design of this microstrip line here. So this, as this one is the structure of microstrip line. So the main parameter to design the microstrip line here, you can see the d epsilon r designing parameter and width of the transmission line. So this is a substrate, we can say, and this is the width of the strip line. And now the thing is, because this one is the interface of two media, so we can have some effective relative permittivity which has the both effective relative permittivity is defined by both the relative permittivity of the media, such as substrate relative permittivity and air relative permittivity. So we can consider this transmission line in similar manner, like by taking the effective permittivity, effective relative permittivity, by considering this formula, we can say this central conductor having the surrounding media is homogeneous as well. Now the thing is, as you can see here, this is a, we can divide just a minute, we can divide this effective relative permittivity in two sections. This is first section and this one is second section. So superficially I will tell you this value is very low. So we can consider epsilon effective is the average of average of relative permittivity of the substrate and air. This is the average. Now this value has very low. So if so, we can say the effective relative permittivity is lie in between lowest one and the highest one. This is the effect relative permittivity of air air, and this one is the effective relative permittivity of the substrate. So it lies in between these two values. Now you can focus here in the formula. The main parameter here is W and D. We can say W by D ratio as well. So here you can see this is epsilon effective is proportional to, we can say, 1 by root 1 plus 12 W by D as well, right? So W by D, if you increase, this value should be decreased, and if this value should be decreased, then effective relative permittivity should be increased, and vice versa, right? So our here we have mentioned here, as we already discussed, the microstrip line has the quasi TEM mode again, right? So here we have I have mentioned 2 points here, the first one and second one. Higher the relative permittivity of substrate, more concentrated will be the field inside the substrate. As we discussed earlier, most of the field is confined in the dielectric media, as we similarly as we have seen in the capacitor as well. So higher the WYD, as we mentioned here, higher the WYD, lesser will be the fringing field. This is the another condition, because effective relative permittivity increases, and due to the increase of effective relative permittivity, more of the electric field confined in between. Most of the electric field confined due to this having the more effective relative permittivity, and due to which we have a less fringing effects. So this is the main advantage of having the higher effective relative permittivity of the substrate. Next, the design equation, as we discussed in the last slide, the main parameter is again W, D and epsilon R. This is the these all are the empirical formulas to have the characteristic impedance of transmission line, that is represented by Z0. This is a characteristic impedance of microstrip line, right? So this is a empirical formula we have. For the case of W by D should be very less than equal to 1, and for W by D is greater than 1. So initially we know the value of in the designing, because initially we need to take a substrate according to our applications, our requirement, whatever we are designing the component of the microwave. So the thing is, as you can see here, suppose if I remove this part, because this part is having the very lower value, we can say if W by D is very less than something, so only this section we have here. So we can say superficially that Z0 inversely proportional to 1 by W by D, we can say, or we can say Z0 proportional to D by W. That means if this width of the transmission line or center conductor increases, the characteristic impedance of the transmission line will decrease. Now and vice versa, we can say if you decrease the width of the transmission line, we have more value of characteristic impedance of the microstrip line. And why we are not disturbing D, because D, the thickness of the substrate cannot be changed if you, once you select the substrate size. So this is the formula if we know the W by D initially. Secondly, suppose if you want to design a required impedance transmission line, means microstrip line. Suppose if you want to make a 50 ohm transmission line, so you know initially the Z naught of the means characteristic impedance of the microstrip lines, for which we have another formulas. W by D is less than 2 and W by D is greater than 2, and for which you need to calculate A and B constant value, which is depend on the effect relative permittivity of the substrate. Here is formula, and second one also dependent on the relative permittivity of the substrate. So based on this equation, we need to understand how to design the microstrip line parameters. So one example I will discuss here. Using a substrate of dielectric constant is equal to 4, that is epsilon r equal to 4, thickness D is equal to 1.6 mm, design a 50 ohm microstrip transmission line with W by D is greater than 2. So according to the requirement of the question, we know W by D is greater than 2 and you need to design 50 ohm transmission line, and we have the substrate parameter as well. So from the last equations for W by, we need to take this equation here for W by D, this equation, because W by D is greater than 2. So in this equation we have some constant. This equation mainly depend on B here, and first equation depend on A here. So we need to find the value of V. This is 377 pi upon 2 Z naught under root epsilon r, where we know the value of epsilon r according to the question. Epsilon r is equal to 4. After putting the value of epsilon r and Z naught, you need to consider 50 ohm here. So I will get the value of V is equal to 5.92 here. Now after getting this value, you need to get W by D ratio by using this formula, and we have the value of 2.92 here. So as we W by D is equal to 2.92, and we know the value of D according to the question, it should be 1.6 mm, and after applying this 1.6 mm we have 3.28 mm. So this width for the 50 ohm should be equal to 3.28 mm. This is the designing parameter of this microstrip line. If you design, if you take or design W is equal to 3.28 mm, you will have the characteristic impedance of microstrip line is 50 ohm. So the question arises here, why we mostly cases we consider 50 ohm here, because most of the connectors in the market available for 50 ohm impedance. So because if you connect the if you apply the source with the help of connectors, so you will have some kind of it can be possible to have some kind of mismatching in the impedance of the connector and microstrip line. So if you take in most of the cases, if you take the 50 ohm transmission line, so there won't be a mismatching in between my connector and transmission line. So most of the connector in the commercial market are available which is 50 ohm to have the less reflections through the strip line we need to design 50 ohm transmission line, microstrip line. This is the main point that we need to highlight here. Surface wave loss. As you know that there are two kinds of losses, three kind of means ohmic losses, dielectric losses, and surface wave loss. So surface wave loss here, so as we discussed in the first or second slide, surface waves always occurs at the interface of two dielectric media. Here in the microstrip line, two dielectric media, this is the interface. This is the interface. So surface waves always lie at this surface. So this is for the grounded dielectric state slave, the cutoff frequency of lowest order surface wave mode is 0. The cutoff frequency of the next higher order mode is Fc is equal to C by 4d under root epsilon r minus 1. So the thing is, in the research point of view, this surface wave should be as low as possible. Most of the researchers are doing the research in this field as well. So this is the drawback, or this is the some kind of, we can say, this should be minimized. Our requirement should take should consider or should minimize this surface wave. So what the initial phase, what we need to consider here, this is the cutoff frequency of the surface wave from after this cutoff frequency, more surface waves will occur. To have a less surface waves, this cutoff frequency as high as possible. So you can see here in these two formulas, you can see here Fc inversely proportional to D and Fc also inversely proportional to under root epsilon r. To have the more cutoff frequency of surface wave, that is higher order cutoff frequency, higher order mode cutoff frequency. So to have to make it more cutoff frequency, this thickness of the substrate, D is the thickness. So thickness of the substrate should be as low as possible, so that you can make the cutoff frequency of higher order mode of surface wave will increase. And if you take the low value of effective relative permittivity of the media or substrate, you will have again high cutoff frequency here. So our main aim is to make the cutoff frequency of surface wave as high as possible for higher order mode, to minimize this surface wave at the interface of substrate and air media. So this is the all about the surface waves. So this is the topic of research. Most of the researchers are doing the research in this field as well. So next one is the loss reduction. As we discussed earlier, radiation loss and surface wave loss. And the last slide we discussed, for to minimize the surface wave loss, low permittivity substrate we need to take and thin substrate, because Fc inversely proportional to D and Fc cutoff frequency is inversely proportional to epsilon r. From these 2 points we can say the surface wave loss can be minimized. Secondly, the radiation loss, as we discussed, the fringing field can be minimized by taking the high dielectric constant, means high dielectric substrate, and thin substrate as well. and the first one is rounding or tapering of discontinuities as well. Mean you can reduce the radiation loss by tapering the transmission line. That means this kind of transmission line and this kind of transmission line, this kind of transmission line having the less radiation loss, and this kind of transmission line having the more radiation loss. So this is all about the thing of microstrip transmission line. This is the side view, front view of the transmission line. Next one is the mode symmetry. The thing is various kind of modes we can have: TE mode, TM mode, as we discussed in the first or second slide. So microstrip line having the fundamental mode or higher order mode as well. So fundamental mode, we can say a dominant mode as well. Dominant mode is the mode which has the lowest cutoff frequencies, so through which from where the propagation gets started. So here we can see here this is the fundamental mode of the microstrip line as we have here. So this is a kind of symmetry in between the field, electric field here, and you can see this is a even symmetry. So fundamental mode always having the even symmetry, and this one is a higher order mode. We can say here we can consider only the negative, 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 and this one is always positive, 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 positive. Or we can write in reverse method, microstrip line having the positive as well, and corresponding to we can take it negative as well, right? So always in the fundamental mode it goes upward or downward, like in this fashion or in this fashion for fundamental mode, right? So this one is the even symmetry mode. Here you can observe here this is a higher order mode. Here this one is, you can take it plus, minus, plus, sorry, this one is plus, minus, minus, plus. So this one is a higher order mode. Also we can say this one is the odd, this is asymmetric, or we can say odd. So you can take it, this one is odd symmetry. So this mode is known as high order mode. So even mode and odd mode we can clearly see here. So we can say even mode is a fundamental mode, or fundamental mode is known as dominant mode. Now the effect, this is the graph showing the effect of effective relative permittivity versus frequency for the microstrip line. Right. So here we have taken the three cases: epsilon r equal to 10.2, 6.80 and 2.33. So here you can see here, this is the effective relative permittivity as we have discussed in the last slide. So effective relative permittivity also depends on the frequency. So this is a graph of frequency versus effective relative permittivity. So you can see here it starts from 9 to 13 frequency range, and from 0 to 12 here. So this is effective relative permittivity. Here you can see up to this point there is a little bit change. It is varied. It is varying with respect to the frequency, but from this point at a certain location of the frequency it gets saturated, right? So at lower frequency from below, then we can say less than 11 gigahertz, it depends on the frequency, but at higher side it gets saturated. So we can say the dispersion effects can be possible at the in this frequency range, because all the parameters is depend all the parameter depends on the effective relative permittivity. So in this region, the microstrip line has some dispersion effect. We can say dispersion effects. Dispersion is known as when the parameter of microstrip line depend on the frequency, dependent on the frequency. This is known as dispersion effect. Right. So this is all about the thing of effective relative permittivity versus frequencies. So here the values get saturated. The same value we have 10.2, 8 point something. You can see here, if you take 10.2, 6.80, and this one is 2.33. This is all about the microstrip line. So finally, we can say microstrip line is a planar transmission line which is useful for the designing of microwave components, means to give the power supply or to activate the microwave components such as low noise amplifier, or we can say antenna as well, and filters, etc. So for this we need to understand how to active all the microwave device with the help of microstrip transmission line. This is all about the microstrip transmission line. Thank you.